Perfect. So yes, thank you very much for organizing this. It's perfect for me at this moment because we're finalizing our work on the relationship between consciousness, the quantum, and integrated information theory. And so I'm very happy to be able to present our recent work to you. So my talk will be separated in two parts. The first part will be about extending IIT's formal framework to finite quantum systems. And this first part is a bit more technical, and I do hope to get some feedback from people that know a bit more than I do about quantum information theory. And if not today, then please send me an email. And if you hear or view this later, the same applies. Okay. And the second part of my talk will be more focused on IIT's implications for a proper ontology and the implications of that for quantum physics. So the second part is a bit more philosophical and speculative. And I also have a disclaimer in that what I won't talk about is whether quantum effects play any role in the normal functioning of the brain. Likely not, given that the brain is a wet, hot, mushy thing, right? And I'm also not going to talk about whether consciousness collapses the wave function. I very happy about Kelvin's presentation, and it's very exciting, but whether consciousness collapses the wave function or not is like, this is not implied by IIT and is also not required by IIT, right? So what is IIT anyways? So I'm very grateful for Leonardo and for Kelvin to already have introduced most of the background for me. But just briefly, I want to highlight a few points, and that is that what IIT is really trying to do is to account for experience itself. So I will use experience and consciousness and phenomenology as equivalent. So we hope to account for what consciousness is, why it feels the way it does, and why it has to do with some parts of the brain rather than others. As Leo said, IIT starts from phenomenology itself and asks what it is. And so it asks, what do I want to explain in the first place? Like, what is consciousness, right? Starting from phenomenology. And the first obvious thing to say about consciousness is that it exists. And the existence of consciousness is also the only existence that we can be sure of, that is immediately given to us and is indubitable, as worked out by Descartes. And so, for example, that there is a physical world outside of our experience that is ultimately merely an inference from within consciousness. And it is what we call an inference to a good explanation, right? Because we want to account for the regularities that happen within our experience. And a very good way to do so is by postulating this outside world that then can explain why we see the things we see, right? So the next question then is what characterizes experiences? So what are the essential properties of any experience that cannot be doubted? And those are the axioms of IIT. You've seen the slide before. And right, so there are one plus these 5 properties. So consciousness exists, and it exists in specific ways that define its character. It's always intrinsic. It is composed of different things. It's specific. It is what it is, right? It is integrated, which just means it's one, right? And it is definite. So it has borders. There's content that's inside my experience, and then there's stuff that is outside of my experience, right? So for example, I cannot see what's going on behind the back of my head. And these are, again, these are very simple properties. Denying them would lead to a contradiction. That's the premise here. So for example, if you take integration, the fact that experience is unitary, if you wanted to negate that and say, for example, that you have 2 separate parts to, that would just imply that there are now two consciousnesses and not one. So it's impossible to have one consciousness that isn't integrated, right? It's not one. These 5 properties are also considered sufficient. So if something has these properties, then there is an experience according to IIT. But, you could also say, how are these properties that are special to IIT? In a way, these are just properties of anything that exists as one thing, but, from its own intrinsic perspective, and that's the intrinsicality here. So consciousness is in IIT is really equivalent with intrinsic existence, the existence of a system for itself, right? And so we're trying to translate these essential properties of experience into essential properties of a physical system that a physical system must satisfy in order to be a physical substrate of consciousness. And so just as the experience itself, a physical substrate of consciousness must exist, and existence in physical terms is defined as having cause-effect power. So being able to take a difference and make a difference. The system must take and make a difference on itself. That's the intrinsicality. It must have a causal structure to be composed of different things. It should be specific, integrated, and definite. Right? And so there, in the end, there should be a one-to-one correspondence between properties of the physical system, the causal properties of the physical system identified with the IIT algorithm, and the experience of the system. So let's have a brief look again at the exclusion postulate because it's relevant for what's coming next, in the sense that IIT does not presuppose a particular spatiotemporal grain for consciousness. So IIT doesn't start with neural networks, for example. It doesn't imply that you have to have a brain to be conscious. Instead, in principle, it should be, the formalism should be applicable across all the various scales, and we find the spatiotemporal scale at which a given system, a given set of, let's say, micro units, experiences is conscious at the scale at which the integrated information of that system is maximal. So another way to illustrate this is here. So we have all the different scales of the system. We can express the same system in coarser or more fine-grained ways. At each of these levels, we can see the interactions between the parts described as conditional probability, so transition probability matrix. And we can evaluate phi for this system at this level and see where it peaks. Now, also, as is implied here, IIT views physics as conditional probabilities all the way down, basically. So even the microscopic level should be describable in this way. And there are no intrinsic properties of stuff that is relevant to IIT. So it's just conditional probabilities is what physics ultimately is. That is an assumption. That's the physicality assumption to get the whole thing off the ground. Right? Now, this picture, though, does imply that IIT should be applicable from the microphysical to the macroscopic. And it is for that reason that we have attempted to extend the classical IIT formalism to the quantum realm, because, we should be able to get a value for a quantum system. Now, one thing I want to clarify is that it's actually a prediction of IIT that we do not expect the integrated information of a quantum system to be very, very big, right? Because ultimately, there should be room for causal emergence. At least, if we would take a quantum description of our brain, that should have a smaller phi value than if we have a description of that system in terms of, let's say, interacting neurons or groups of neurons, whatever fits the spatiotemporal scale of our experience. Now, that said, here is our recent work, aims to translate the mechanism integrated information that Leonardo presented into a quantum mechanical framework. And maybe one more thing to say here about information in IIT in general is that IIT's notion of causal information differs quite a bit from standard information theoretical measures. First of all, it is intrinsic, and that is what is described here by the intrinsic difference measure, the work that Leonardo presented. It's evaluated from the perspective of a mechanism within the system, not from the perspective of an observer of the system, right? It's also state dependent, and it is causal, which means that it's evaluated against all possible counterfactuals of a system transition. And it is also irreducible, which means that it's evaluated against the partition of the mechanism into independent parts. So this is joint work that I've been doing with Robert Prentner and Ian Durham, who's with you in the room and will talk after me. There has also been some prior work on translating or applying integrated information into the quantum realm. So Max Tegmark tried to evaluate the integrated information of a quantum spin system, for example. And then there's maybe the most direct translation so far by this paper by Zanardi et al. That they basically described how you could translate the IIT 3.0 formalism to a quantum system, and that's been explored a bit more by Johannes and Sean in this paper here. So what did we do on top of that? Well, first of all, there is a 4.0 version now, and we try to stick to the principles that are worked out in the new version. The second point is that none of the prior works was convergent in the sense that, it was just more like two different implementations. There was a classical version and a quantum version, but they didn't converge. And so we really tried to have a quantitative convergence. So if you use the quantum IIT and you input classical states, you should get the same values as for the classical, comparable systems, and thereby we have to enable a direct quantitative comparison, which is necessary to move across the levels of description. The third point is that we translated this measure of intrinsic difference, which I hope will be useful even outside any quantum integrated information formalism, just as a additional measure of information from the perspective of a mechanism or a qubit or a quantum gate within the system. And finally, we've extended the notion of conditional independence to accommodate entanglement. So what does it all mean? So let's start here. So what did we do? It's a pretty straightforward translation from principles of classical information theory to principles of quantum information theory. So when on the classical side, you have probability distributions, in the quantum mechanical description, there are density matrices, right? Then there are classical measures of a difference between two distributions, and maybe the most famous is this, the Kullback-Leibler divergence or relative entropy. And the intrinsic difference measure is related to this Kullback-Leibler divergence, formally related, in that you could view the Kullback-Leibler as an average over this term, the state-wise mutual information here. Whereas the intrinsic difference sort of doesn't do an average over the states in the distribution, but picks a particular state. the one that maximizes the difference between the two distributions uses that as the information value. So now, luckily, there is a direct translation of the relative entropy into quantum information theory based on the von Neumann entropy. And you can input to density matrices, and you can see you get a measure of the difference between them. And now, if we express those density matrices in a way that is, if we diagonalize them and then compare them, this can be done in a relatively simple way. And so all quantum states, pure or mixed, can always be diagonalized, and then this measure can be computed quite straightforwardly. Now, how do we get from there to the intrinsic difference? Well, we just do the same thing as in the classical case. Instead of the sum over these terms, we use the maximal state. So what you get in the end is a measure that compares the difference in probability between the one quantum state and the other quantum states in the eigenstate of the first matrix, where the difference is the largest, right? And so this measure will now coincide with the classical one if rho and sigma commute, and this basically means if they're in the same basis, right? So then this converges to the classical formulation. Now, the second, a bit technical aspect that I wanted to highlight was this notion of conditional independence, because in a classical physical system, the way that we require it for the IIT formalism is that, so we want to start with a system that is a neural network, for example, and it's made out of units that are interacting. And those units, the way they interact should correspond to a causal network. So there are actual causal mechanisms. And a property of causal mechanisms is conditional independence. That means that given the past state of the system, I can compute the next state of each individual unit within the system without knowing any of the other units at the same time point, right? So it means that there should not be any instantaneous correlations between the units of the system. Now, this property is obviously violated by quantum systems when there is entanglement, because that is what entanglement is a correlation within the same time points, or between two units of the system, right? So we have to revisit this assumption. And on the other hand, this assumption is quite relevant for causal analysis when we want to assess how much a subset of a system constrains another part of the system. And as an example here, I want to briefly walk you through this two logic gate. So this would be a copy gate, and this would be an XOR gate. And here you see the logic function. And with the IIT analysis, and I hope that makes sense to you, we get a measure of the effects of A, B, and AV onto C or D. So given that A is in state 1 at time t, it constrains C to be on at the next time step, right? And A and B together also have constraints here onto the XOR. And an important thing now is that, however, B by itself doesn't constrain anything. And I hope that makes sense. So if you have an XOR and you only know B, you cannot predict the output of the XOR because it depends on A. But the only way to get this result really is by causal marginalization, or you have to marginalize A. So if you flip the state of A, so if it can be either 0 or 1, and you don't know which, then B alone is not sufficient to give you any prediction about B. However, if we now look at B's prediction over C and D, if all we do is marginalize A, we will get a correlation between C and D, right? Because A sends common inputs to C and to D. And we're still only evaluating the constraints of B. So now it would be wrong to attribute this correlation in C and D to be an effect of B. And so in order to not make this mistake, what we have to do is provide independent noise inputs to C and D here. So we basically split A into two things and give independent inputs to C and D. And if we do that, we can see that there really is no effect of B on C, D, or the two together without knowing A. And we find that there is no integrated information of B as a mechanism by comparing it to the full partition, which here has the same value. Now, this copy XOR system, this classical system, is in fact equivalent to a C0 gate, a quantum gate, if you input the same classical basis state. So as I said, we want our quantum IIT formalism to be convergent. So what we want is to get the exact same results for this quantum system, given that we input a purely classical basis and the output is also classical. So this means, in this case, that causal marginalization is still required in the quantum formulation to discount extraneous correlations. And extraneous correlations would be here, any influences from A when we evaluate the effects of B, right? On the other hand, we can input a different state and get a different result. So here, a mixed basis input would give us the Bell state, right? So this is a property of the C0 gate. If you input the +0 state, what you get out is a perfectly entangled quantum state across the two qubits. And so this means that, and so here, if we apply the quantum IIT analysis, the result we get, and I hope that result seems sensible to you, is that only the two together have an effect on the two outputs together because they're entangled and there is no information of the individual qubits after the application of the C0. So on the one hand, we want the causal marginalization. On the other hand, entanglement should be maintained. And so the way we work this out is by having an additional step in the analysis where one first has to identify the entanglement structure of the system. So we want to identify the maximal partition of the state, the current state, or the quantum state of the cause or effect repertoire. So what is predicted or retrodicted, and see which qubits or qubits or whatever are correlated in which way. And so analyzing that may be tricky, especially for mixed states. For pure states, it's fairly easy. But so this is the first step. We identify the entanglement structure. And then as a conceptual decision, we treat entangled subsets as indivisible units and enforce the conditional independence between those indivisible units, right? And you can see that here as a product over the parts of the cause and effect repertoire. By doing so, we can quantify the effect of a subset of a quantum state onto the results after applying a quantum operator. Right? Okay, and finally, I want to mention a potential nice application of our work even outside of IIT. That is that the compositional nature of IIT can be paired with just applying the IIT formalism with an identity operator, and thereby we can reveal differences in various kinds of entanglement between quantum qubits, for example. So let's first take a completely classical case of 3 qubits. If we apply the identity operator, nothing happens, right? Everything stays the same. And what we would get from the IIT analysis is that every bit sort of implies itself, right? Because it stays what it is, basically. Now, for 3 qubits, we have one kind of entanglement of maximum entanglement. That is the GHZ state. That is basically an extension of the Bell state. So we are either in all zeros or in all ones. And it's a superposition of those 2 states. And now here in this entangled state, there is no structure to be found, right? It's only the whole system that causes the whole system, but there's no substructure, sub-information structure here that can be identified. This is very different from another type of maximally entangled state, which is called the W state, that is constructed in a somewhat different way, where you actually find all possible constraints across all subsets, across all orders. So the individual elements have a constraint pairwise. There are pairwise constraints, and there's an additional constraint, additional irreducible constraint by the system as a whole. And now for those that are into information theory itself, there's something that's called the partial information decomposition. So you might notice that these values, they don't add up to 3 bits, to the 3 I bits. So we call them I bits for intrinsic bits. But and this is how it should be, because of course there's some redundancy in these predictions, but they're nevertheless there. So the question we ask or answer is, what are the constraints of each of these subsets taken by itself with no knowledge of the rest of the system? Okay, so to summarize that part, the positive takeaways is that we constructed this quantum integrated information for a mechanism within the system in the latest formulation of IIT. It converges to the classical formulation for classical systems. We have a new measure, the quantum intrinsic difference, that hopefully will be useful beyond IIT. And we were able to extend the notion of conditional independence to accommodate entanglement. Now, what I found especially nice is that some of the intricacies of the classical IIT formalism actually resolve itself in the quantum case. So there's a sense in which it gets easier when we go to the quantum level. And one point here is, for example, that we sometimes get this feedback that, oh, according to IIT, because you have to test all these counterfactuals, consciousness depends on states that never happen, right? But with the quantum operators, that's how they're naturally described, right? So counterfactuals are naturally captured by quantum operators, because what quantum operators are in the end is just a transition probabilities. Right? Also, we have this technical point that when we consider the interactions within the system, we set all the outside universe as a fixed background condition. And in the classical case, that can sometimes seem not to be the right thing to do, but in the quantum formulation, we actually have, so the fixed background condition fits very well with the non-communication theorem, which means that a local operator won't change the state of the environment. And so keeping the states fixed across the conditions, or from the transition from T to T+1 actually makes perfect sense here. And as a last point, with the classical formulation, the unconstrained cause repertoire is always at maximum entropy, but the unconstrained effect repertoire is not always, because it's constrained by sort of the mechanisms which can have convergence. But because all the quantum operators, at least in the unitary transformation that I've been talking about so far, is reversible, and then we have maximum entropy both on the cause and the effect side. So, however, there are also problems, and one of the big problems is that we, so far I've only been talking about unitary transformations. So just dynamics, quantum dynamics, right? And if we now want to apply this quantum IIT measure to the post-measurement state, we run into trouble, because while I can make a prediction of, the state here will constrain the output of the measurement to some extent, not always, but often, the state here actually does not constrain what happened before the measurement. So even if I know that a measurement happened, I cannot say anything about which quantum state I came from, not from a single observation, right? And IIT is always about a single thing, because it doesn't make sense to, compute the IIT value of an ensemble, because we want to know the consciousness of a set of qubits, right? So not of an ensemble. So what do we do here? So I came up with 3 ways to go forward about measurement given this dilemma. So one is that maybe there is no such thing as collapse, right? Which is a proposal from the many worlds interpretation. Second possibility is that collapse is ultimately a physical process that isn't random, so that retrodiction would be possible, and then you could have a phi value larger than 0 also after the collapse, which would then not be, or which I don't know if we should call it collapse then, but after this process. And the third option is that, well, we didn't expect quantum systems to have very high phi in the first place, so maybe we just have to go and look at macroscopic processes and recover a positive phi value here. So this is definitely something that I want to continue to explore, and maybe is the most straightforward way of resolving this problem. But I want to spend the last 5 minutes or so on this point, the no collapse idea, and to highlight a bit in which way it is not yet coherent with consciousness, at least from the perspective of IIT, but also I believe in general. And I do want to say that this is obviously the part where I am wildly speculating, and I'm not an expert, so this may all be me just not understanding how decoherence works yet, but please tell me, So the starting point of the issue is that IIT ultimately implies an ontology. So what IIT is all about is phenomenal and physical existence. So phenomenal existence is that the experience exists, and IIT says that it is identical to this phi structure. So for Kelvin, we actually went with something simpler now. It's not phi shape, but phi structure. Right? And this phi structure is what is there physically, right? So there, whereas there is a substrate, which is what all the rest outside the Tononi lab would call physical. But that is actually just something that we usually interact with, we manipulate and observe it. But what is really there, according to IIT, is this cause-effect structure that can be unfolded from what we observe about the substrate. So again, there are a few things that are important here in this picture. One is that it is critical to realize the ontological primacy of the phenomenal existence, right? So that is what that is the only existence we actually know of. And so consciousness is real, and you have to find it somewhere in your physical model, right? The second important point is that the substrate itself is purely operational. So even physically, what actually exists is the cause-effect structure. And so one of my pet peeves about theories of consciousness is that there is a very simple test for any theory of consciousness, and that is the the individuation problem. So let's say we have 3 people in a room and we ask, according to theory of consciousness X, how many consciousnesses can you identify? This is a very straightforward question, and yet almost no proposal to date has the theoretical tools to approach the individuation problem without presupposing brains as the seats of experience. And here, so what is the problem? Well, we have a bunch of, stuff interacting, right? And if we view this at the microphysical level, it's all just little things interacting. So how do we even find the brain in the first place, not alone like consciousness? So IIT here has a way to say, well, we can identify maxima of integrated information that are maxima of systems that constrain themselves over, their interactions with the environment. And so in principle, IIT should, in this room, identify these 3 big consciousnesses, and then possibly many tiny little consciousnesses that we call sort of ontological dust. So everything should get subsumed, but some things might just be, nothing really. But right. So now, given this picture, given that consciousness exists, in the many worlds interpretation, however, the entities need to be found within the states of the superposition. So what I drew here is that the whole thing here is the wave function, and the yellow panels are all the individual states of the superposition, all the branches, right? And so there are millions of branches, but ultimately we know, because consciousness exists, that our consciousness would have to be found within a branch, right? However, if I just take our quantum IIT formalism and I apply it to the system in a state, then I would not apply that to the states within the superposition, but to the actual wave function. So to explain this, here I have a very small system, 2 qubits, that's my universe, and it evolves according to this unitary transform, right? And it's this mixed basis state, so I can write this quantum state as a superposition in the classical basis, or I can also write it as a superposition in the plus minus basis, right? And those are equally valid, and they depend on the basis. Now, if and I should also say that whatever universal Hamiltonian we have, it applies to the wave function as a whole, right? So the updated form of the universe does not apply individually to those states in superposition, but to the whole thing, right? So what would justify us to look for entities within each states of the superposition? Because so this is something that occurred to me just developing this quantum information theory, is that we take the wave function and plug it into the IIT formalism, right? Which then, this is also something I wanted to say. So the opposite of what Kelvin is trying to do, right? So Kelvin takes the wave function and plugs in classical integrated information values, right? Whereas we have the integrated information formalism and try to plug in the wave function. So that would mean that if we worked it all out, there are possible entities here, the 1 qubit, the other qubit, or the 2 qubits together. And whether they are in a superposition or not doesn't matter. Like, we're identifying subsets of the system. And the least we would need to go look here is just another principle that, however, then seems to be a bit ad hoc if you wanted to apply IIT here within these branches. So that's something I wanted to say as the criticism possibly of the many worlds, or ideally much rather I would want to get an explanation for how this is supposed to work. Now, the last slide here is just to spell out the ontology a bit more in comparison to what people typically think, right? Because so this is the IIT ontology, which we call the intrinsic powers view. And by the way, everything about the ontology should appear shortly in an IIT paper about free will that we hope to upload within the next week or so. But how people typically think is that you have this substrate, and the substrate is what really is real, right? This is physics. You have the brain, you have neurons interacting, atoms, and so on, or a wave function. And then somehow there's a corresponding functional state that is determined based on the interacting microphysics here. And that functional state sort of corresponds to our experience, our decisions, our thoughts, and so on. And the problem here is that whatever that functional state is, necessarily is always epiphenomenal, right? And so that's why this kind of compatibilism, or saying that this is equally real, always has this issue in that, no, it's not the same, right? This is somehow privileged, that ontological, the substrate is taking as the thing that really exists. And by contrast, IIT comes in and says, no, what really exists are these cause-effect structures, and we have these entities, and all we have is interactions between the entities. And when we do physics, what we do is we interact with this operational substrate. It is, we get our answers by manipulating and observing these units. But what really exists is the causal powers, the causal structure between these units, right? And everything here is perfectly compatible with physics. There's no need to violate causal closure. And yet, this is not a view that implies that consciousness is epiphenomenal, because the substrate actually doesn't exist, right? So there's no sense in which this is epiphenomenal. And consciousness really is the way to see that this picture isn't just a nice story, but rather a fundamental description of what there is really, right? Because we know, again, the starting point, coming back to the starting point, we know that consciousness exists. Okay. And that was my last word, and I want to thank you again and everyone else, and I'm very happy to take questions now.
Sure. So we'll start in the room with Johannes.
Yeah, thanks very much. Can you hear me, Larissa?
Yes.
Yeah, so thanks very much. Very interesting perspective. So I have a question about the very last slide, so maybe could you show it again?
I'm trying.
The logical slide. But this is really something I never understood, and so it's a wonderful opportunity to ask it. So I don't understand why, if you take the left-hand side view, why IIT has the form of a mapping, like very abstractly speaking, from a physical description of things to cause-effect structures.
Why there is a mapping from physical?
So is it that if consciousness, or I mean phi structure, whatever, is what exists really, why is sort of the formalism of the theory a formalism that you would see in physicalist theories and supervenience theories and theories that describe the physical as closed? So why is there this sort of tension between the ontology and the formalism?
Well, so the formalism, right? I should start a bit earlier. So So we start with consciousness exists, right? And we want to find, and as I said, that there is a physical world in the first place is an inference from within consciousness, right? But it is what Leo also highlighted. It's this principle of a principle of physicalism and realism, right? So actually, the principle of realism. If you don't assume that there's something outside your experience, right? You're done. You cannot do anything, right? So if you want to do science, if you want to come up with a theory, you start from consciousness, but you have to. Your next step is that you have to postulate there is a world out there, right? So we're trying to map then consciousness onto this substrate that we can, interact with, manipulate, and observe, right? And identify what in this world, right, corresponds to consciousness. And so ultimately then there is this identity between consciousness and this cause-effect structure that we get. But it's an identity that is not reductionist, right? So it's not that once we find the physical thing, we have explained away consciousness. That's impossible, because what we started with is that consciousness exists and it is what exists, right? So the whole purpose of the formalism is to sort of unpack cause-effect power. Now, maybe, and interrupt me if I'm going off your question, but one thing that comes up is, okay, but I can also take, I can take, and we do all the time, right? I can take a made up TPM and I can run it through the algorithm, right? But you can do that because the algorithm isn't IIT, right? So it's also, I guess, with information theory, you can analyze probability distributions, or you can analyze causal models, right? And if you apply information theory in causal models, you get causal answers. If you apply it on Bayesian networks of abstract variables, you get abstract answers. And the same is true for consciousness. So if I apply it to the microphysical substrate and the proper black boxings of those, I get consciousness. If I apply it to something simulated, I get something simulated.
Okay, next question from Dave.
Just a follow up on Johannes. I'm also interested in this question. Yeah, you might have thought that given that consciousness is primary in this ontologically primary on your picture, then the theory could have taken the form of, instead of a mapping from physical processes and cause-effect structure to consciousness, we'd have a mapping from consciousness to cause-effect structure and to physical processes. And certainly if consciousness is ontologically primary, we should expect that such a theory would be possible. So is there a way to formulate IIT so it takes the form of a mapping from states of consciousness to cause-effect and ultimately to states of the physical world, or is that impossible for some reason?
So, I mean, in a way, that's what it is, but it's only the case for, so we start with consciousness, identify the essential properties, right? So we're asking what is consciousness, and we do that in the phenomenological realm, right? We're not starting by asking what do we need physically to make a conscious system. We're actually asking what makes consciousness consciousness, right? The defining properties. And so these defining properties get like translated in the direction that you said, from phenomenology to physics, right? Or then, yes, physics. What we didn't constrain is all the specific properties of a given experience. And so that also captures the question by Don earlier, like to what extent is this cause-effect structure explanatory in the end, right? So with the cause-effect structure, certainly the space project was the first example of trying to do that. Again, the question is, what is spatial extendedness from within the experience? Well, what we're doing is we analyze, what is required, or how does it really feel like to have spatial extendedness, and what are the properties of spatial extendedness, and then try to have a substrate that can capture that. So there is the opposite side direction of inference also, but we cannot do that for everything because first reason, because we have limited introspection, and also it could be wrong, right? This is maybe also a point that Leo made nicely, but it's often missed, is that it's not that so obviously you need to have introspection to create a theory like IIT. You have to be able to reason and to do all sorts of do math, and but the axioms themselves are indubitable in the sense that like negating them leads to a contradiction. So they're not actually introspective, with maybe the exception of the composition axiom, right? So what I'm trying to say is, even though introspection can be wrong, and therefore the specific properties that we identify by like thinking about our experience may be wrong, and therefore are not taken as axioms and starting points necessarily. The axioms, the defining properties of the experience are not frail to this sort of almost illusion. Yes.
If I could follow up on Dave's question and try to distill from you a short answer. Why didn't you draw the curvy arrow in your left-hand diagram in the downward direction rather than the upward direction? Because it seems like in verbally you're saying that you agreed with what Dave asked, that we start with consciousness and we derive the quote unquote physical, which I think is the cause-effect structure that you're calling manipulation and observation, going the right and left way. But then you have the curvy arrow going up to phi structure as if it is derived from the more basic manipulation and observation.
Right. So it's not derived, it's unfolded. It's operational, right? It's what we can do. So we're as scientists are this black person, here the shadow person, and we're the outside observers that in order to do science, right, on this thing, we have to start here and perform this operation. The system itself doesn't have to do that, right? So there's no operational error that goes from here to here without the external observer. Also, could you identify yourself? Because I don't know who I'm talking to.
Chris Fuchs.
Okay, thank you.
Okay, we've got to move on quickly. If I could just insert myself, I'd just like to ask a quick question. This is Calvin, by the way, Larissa. I just wanted to go back to the problem that you thought collapse theories raised for your idea. So the idea was something like, if you look at the post-collapse state, you can't get any information in the relevant sense about the prior state. And then you thought, well, maybe to get around this problem, we could move to something like a many worlds interpretation. I'm not sure if you fully covered this in what you said there, but I was worried that any problem that collapse theories would raise here would just be the same kind of problem for many worlds theories, simply because consciousness is not going to spread across branches in a many worlds theory. It's going to be confined to a branch. And within a branch, it just looks like you're in a collapse theory. There's not really any difference from...
Yes, but if there is true collapse, the wave function as a whole is the collapse state, right? And so then if I apply IIT to the wave function as a whole, I will only have one of those yellow things, sheets in the first place, right? So I will identify the consciousnesses in the wave function as a whole.
Oh, I see. So you apply IIT to the wave function as a whole, and the thought is integrated information is going to get maximized within branches, not across branches.
No, so that's the problem, right? So I have the IIT formalism. I plug in the wave function. If there's true collapse, right, in the dynamics of the wave function, then I don't have this multiplicity here. I just have one path, and then then I don't have to have this extra postulate of why should I go from applying consciousness to the thing as a whole and sort of identifying me across all the branches of the wave function to like finding me only within a branch, right?
I wonder if you have a version of the how many consciousnesses in the room problem now, because most people would say if many worlds is right, and we typically think of one consciousness for each branch, so you're going to want the formalism to yield not 3 consciousnesses in the room, but 3 million consciousnesses in the room, as it were, one for every branch.
But if you apply it to the wave function,
I don't know whether the formalism is going to have the resources to deliver, one consciousness for every branch.
right, do you need an extra principle? So, right, that does my point. So the least you need is, and this is not just IIT, right? So if you want to identify things that hang together causally well, right? And you're saying, well, I want so there's just the idea of identifying entities within each branch needs a justification that I don't see there to be, right?
Okay, so this will be a radically new form of many worlds interpretation where consciousness is going to kind of cut across branches rather than corresponding to branches.
No, that's not what I want, right? I don't want there to be a consciousness across branches. I'm saying my argument is we know from our experience that if many worlds is true, we exist within a branch. On the other hand, if I start with microphysics, the wave function is real, and I'm trying to identify entities, if that's your starting point, you wouldn't go into the branches. No one would, right? Like the only reason we go into the branches to identify people, right, is because we know that for us, that's how it looks like.